here. And first of all, hi everyone. I hope you and your loved ones are doing well during these difficult times. It's actually a great pleasure for me to introduce today's lead seminar speaker, Professor Kumar. Professor Kumar is a university distinguished professor and a Regents Professor at the University of Texas A&M, where he also holds the College of Engineering Chair in Computer Engineering. Before his current appointment, he studied at IIT Madras and Washington University, and he was a faculty member at the Math Department at the University of Maryland and a faculty member at UIUC. So Professor Kumar has made a number of fundamental contributions in several fields, including seminal contribution to adaptive control, queuing theory, and to the understanding of the scaling laws for wireless networks and for cyber-physical systems in general. So I can probably take a good portion of this hour just by listing the achievements and the awards of Professor Kumar, but I think that's not the goal here. So I'll try to be brief. Professor Kumar is a member of the US National Academy of Engineering, Indian National Academy of Engineering, and the World Academy of Sciences. He was awarded a honorary doctorate by ETH Zurich, and for his outstanding contribution, he received a number of awards. I'm just sampling like 3 of them. The IEEE Field Award for Control Systems, the Outstanding Contribution Awards of ACM SIG Mobile, and the Infocom Achievement Award, among many others. So his current research is focusing on cyber-physical systems, security, privacy, traffic management, 5G, wireless networks, machine learning, and power system. Just a long list here. Today is going to talk about revisiting the trade-off, exploration, and exploitation. And I will stop here. Without further ado, let's welcome virtually Professor Kumar to the LIDS seminar series.
Thank you very much, Luca. I appreciate it. And thank you. It's actually good to see old friends again over Zoom. So I'm going to talk about a problem that I actually talked about at MIT at my first visit to MIT in 1982. I'm going to say more about that later. But this work, as you know, the bulk of this work is done by students and postdocs and so on. And in this particular case, it was done by Shi Lu, my PhD student who is on his way to Facebook, and by Ping Chun She, who was a PhD student from here, then postdoc with me, and now is a faculty member at National Tsingtao University in Taiwan, and also a colleague, Anirban Bhattacharya from the statistics department. Okay, so I actually went back, got special permission and went back into my office to find these notes of my first seminar at MIT in November 9th, 1982, and I'm going to talk about exactly the same topic, okay? So first I'm going to run you through my notes. At that time, it was a Blackboard seminar. I was in a math department, so I decided to do the seminar on a Blackboard. And the topic was optimal adaptive control of Markov processes. And here is the adaptive control problem. So let us say that I have a control Markov chain, and the transition probability from state I to state j depends on a control u. But the transition probabilities are unknown. They also depend on an unknown parameter theta. And let theta 0 be the true value of the parameter, which is unknown to us. And the goal is to minimize a long-term average cost. So there is a cost every time you're in state I and you take action U and you go to J, and you want to minimize the long-term average cost. Later on, I'll shift gears and talk of maximizing long-term average reward, but it's the same thing. And the question was, can we obtain the same optimal value of the cost without knowing the parameter theta 0 as we could if we knew theta? In some sense, that the answer to that is clearly yes, but I want to lead you through the thinking for that. Answer is yes. And this particular lecture was done in a certain context, okay, certain finite parameters and so on. Now, the straightforward method of adaptive control, which is also called the certainty equivalent method, would be the following. For every value of the parameter theta, you determine the optimal stationary control law. So that is a mapping from states into action. And that mapping, the control law, of course, depends on what the value of the parameter theta in the transition probabilities is. And then the adaptive control law is as follows. First, you estimate the unknown parameter theta. And for that, we can just choose a maximum likelihood estimate. So if you have a history of states and transitions up to time t, then you take the product of the transition probabilities, and that's the likelihood. And you choose the maximum likelihood parameter. And then you just pretend that that parameter is the correct value, and you apply the stationary control law corresponding to that parameter. So this is also called certainty equivalence. Now, a fundamental problem that arises here is the closed loop identification problem. Suppose the parameter estimates converge to some theta star. Okay, theta star need not be the true parameter, it could be some other parameter. Then under reasonable assumptions, the control law also converges to that corresponding to theta star asymptotically. And therefore, after some time, the closed loop dynamics of the system are the transition probabilities of the Markov chain under the control law corresponding to theta star. So the probability of going from I to j is Pij under the action phi theta star I, which is the optimal feedback if the parameter were theta star and the state were I, and the true parameter theta 0. So it depends on the control law corresponding to the estimated parameter phi theta star under the true value of the parameter theta 0. Hence, we can only identify these closed loop transition probabilities. Now, since our estimate is theta star and the estimate looks pretty good, it must be the case that we identify the closed loop transition probabilities at least correctly. So basically, the transition probability under phi theta star, when the parameter is theta star, should agree with the transition probabilities under the control law phi theta star when the true parameter is theta 0. So we identify the closed loop dynamics. And this is indeed what Borkar and Varaya proved. This was in Vivek Borkar's PhD thesis. And he showed that, in fact, the parameter estimates converge to a parameter where the closed loop transition probabilities are identified. However, the control law you converge to phi theta star is not necessarily optimal for theta 0, and lots of counterexamples can be provided. The dilemma is this: if the parameter estimates converge and the control law is converging, and therefore you cannot explore other possibilities under a control law that doesn't excite all modes, if you will. Okay. So that's when we came up with this adaptive control law. We wanted to see how can we fix this problem of that Vivek Borkar had identified. And the control law is very simple. For each parameter theta, if you control it optimally, there is an optimal cost. So let J of theta be the optimal cost corresponding to the parameter theta. Now we'll choose a sequence little o of t. Little o of t, of course, means that divided by t goes to 0. But I want it to be a little bit more than that. I want it to be positive and going to infinity at the same time. So a sequence going to infinity, but slower than t. And the adaptive control law, and I'll explain this in the sequel why this is the case. We're just going to slightly modify the maximum likelihood estimate. So the green term is the likelihood, but in addition to that, I'm going to multiply it by a term involving the optimal cost for theta raised to the power minus O of t. If you want, you can think of O of t as log t, for example. So what we are doing is we're giving a slight preference to parameters which have lower costs, okay? And that's called cost biasing, and we'll see why that is eminently reasonable, okay? And then we simply do certainty equivalence. So it's a cost biased maximum likelihood estimate followed by a certainty equivalence control law. And then the main results were that if you do that, then in fact, the optimal cost is, the cost that you incur is optimal. The parameters converge in a Cesaro sense to a parameter, certain parameter, and that control law corresponding to that parameter is optimal, and the transition probabilities, closed loop transition probabilities are identified. And there was a proof of that. And basically, what this thing does, this scheme does, is because of this delicate biasing log by say log t or little of t, it occasionally probes, introduces probing into the system, and this probing is done automatically. Now, this treatment can be extended in various directions, linear quadratic Gaussians, more general Markovian systems, etc., etc. So that was the talk that I gave in 1982 at MIT. And in fact, after my talk, John Tsitsiklis, whom I met for the first time then, came up to talk to me. And I think he was just about to graduate at that point. And I'm giving the same talk after he's now the director of the same lab. Some things have not changed. Okay, so what is going on here? Why am I interested in this problem? So let's take a very special case of this, multi-arm bandits. Okay. So the two-arm bandit problem, all of you know what that is. There are two slot machines, Bernoulli slot machines. The probability of getting a success if you pull the red machine is theta 1, for the blue machine is theta 2, but you have to choose one machine at each time, and you get reward according to those probabilities. Clearly you want to choose the better arm, but supposing we don't know theta 1 or theta 2, what should we do? And one strategy is just to play each arm a few times. That's called exploration. And then after that, choose whichever is better and exploit it, okay? So there's a fundamental trade-off in all these learning come action problems, which is a trade-off between exploration and exploitation. And exploration can be valuable, but it's costly. And what's the best trade-off? And a very topical problem nowadays is, of course, drug testing. So you have two drugs. What drug do you give to patients as they come in? And in fact, the person who actually introduced this problem, Thompson, in 1933, he says that a considerable saving of individuals otherwise sacrificed to the inferior drug treatment might be affected. And I cannot think of a more apt statement than for the current era. Okay. All right. Also, of course, another big commercial success is Google. Google makes about 85% or so of its revenue when people click through on their sponsored links. Now, they get money only when people click, and it's got to decide which links to show. So if you type hotels, it has to decide which hotels to display. But it doesn't know how popular these hotels are, so it's a bandit problem. And that's its biggest revenue spinner. Okay. So if you specialize this cost-biased adaptive control to Bernoulli bandits, and in fact, I did that in a report in 1980, which I never published, and I cannot find it. I think it's in some closet somewhere. So if you have two parameters, two slot machines, theta 1, theta 2, the optimal reward, in this case now it's reward, is the better of theta 1 and theta 2. And supposing you've played arm I, Ni times, and you've had Si successes and Fi failures, then the cost bias maximum likelihood estimate is this. The blue term is just the likelihood expression. If you play arm 1 and you get S1 successes and F1 failures, and the likelihood is theta 1 to the S1, 1 minus theta 1 to the F1, etc. And then the cost biasing is you take this optimal reward under these parameters and you raise it to a bias term, alpha. So alpha is little of t here, okay? It goes to 0 when divided by t. And it turns out that this actually, you can explicitly solve and you get an explicit index, okay? So this is the index of an arm, and you just play the arm with the largest index. So this is what I had in that report. And that was the end of it, and I never investigated any further, okay? So I'll tell you more recent results in a second. But so the question is, how does this compare to what has been done in the meantime over the past 38 years, okay? But before I do that, I want to give you a brief historical account of banditry. So the first mention of this bandit problem is by Thompson, who was in the Department of Pathology at Yale University. And in this pioneering paper in Biometrica 1933, he said, I want to see how I can use data, however meager, as a guide to action. Okay, very topical statement for the times. And he says, it's apparent that a considerable saving of individuals otherwise sacrificed to the inferior drug might be affected. And Thomson actually suggested a scheme, which was the following. It's a kind of a Bayesian viewpoint. Let us say that you start with the beta distribution of the parameters. And let P be, after some number of plays and empirical record, you can calculate the probability that the red arm is better than the blue arm, or the blue arm is better than the red arm. Okay, let capital P be that probability. And then Thomson said, supposing I decide to play arm 1 with a probability that's a function of the probability that it's better. Okay, so with a probability f of p. Then he said, now if arm 2 is better, right, then I'll suffer a loss. And the probability that that will happen is 1 minus p, which is the probability that arm 2 is better, times the probability that I play arm 1, which is f of p. On the other hand, arm 1 is better, the loss would be 1 minus f of p times p. And he said, hey, listen, let me make both losses equal by symmetry. And if I do that, if I choose f of p equal to p. So that's the strategy that Thomson suggested. And he said, play arm I with the probability equal to the probability that it is better. Okay. And this strategy is called Thomson sampling. And in fact, as we'll see, it is still one of the best policies in the field. Thomson actually at that time was interested also in calculating this probability. So the probability that a certain beta distributed random variable is better than another beta distributed random variable. And in those days, there were no computers. So he actually built a mechanical device, okay? So he actually showed that if you take a certain number of blue balls and red balls and shake it up, and he actually built a triangular cardboard piece, then he said, if you count the probability, if you find S1 red balls before S2 blue balls, then that's the probability that one distribution is better. So he just actually shook it up and then did this count and then played an arm, and then he found that he got fantastic results. So he actually built a mechanical computer for Thomson sampling. Anyway, so this whole bandit thing has influenced many, many fields, and I'll just give you a brief survey. Evolution of adaptive sampling. So actually in 1952, Robbins lamented that when sampling was being done, they said the statistician was usually consulted only after the experiment was over. This reminds me a little bit of the complaint of control people. They said only after the hardware is designed, then they come to the control people for the control law. It's something like that. And the first attempt at adaptive sampling was by Mahalanobis in Bengal in 1940 when he wanted to estimate Jew acreage. And it was a pioneering effort in the absence of any theory. And subsequently in 1941, Dodge and Tomic were interested in quality control. So they wanted to know if I produced goods, are the products defective? And they said, hey, listen, so let's do it this way. Take N1 samples. If less than D1 are defective, then say the batch is okay. If more than D2 are defective, then reject the batch. And if it's between D1 and D2, then take N2 more samples. So this is adaptive sampling. And of course, this idea was carried through very completely by Wald in his work on sequential design, okay? All right. Now, there's also a frequentist viewpoint of bandits. And that actually was first advocated by Robbins in 1952, who apparently was unaware of Thomson's work, okay? He said no Bayesian distribution for theta 1 and theta 2. Let us suppose they're arbitrary numbers between 0 and 1, and I want to maximize the long-term average reward. And he said this is represents in a simplified way the general question of how to learn from experience. And by the way, let me just at the same time make some comment about the present day. So Robbins was interested in the long-term average reward being optimal. Nowadays, there's a finer notion of optimality. People actually look at the evolution of the total reward and compare that to the expected maximum reward that could be obtained if you knew which arm was better. So they actually looked at the divergence of the total reward from the expected optimal, and that's called regret. And Robbins' long-term average optimality simply means that regret is little o of capital T, okay? But nowadays, people are more interested, what exactly is this little o of T? Because it's a lot of money for Google, the pre-constants also matter. Okay. Besides the frequentist approach, there's also the Bayesian formulation, and that actually was studied by Bellman in a paper in Sankhya in 1956. And he said this problem is in the general field of learning processes, where we must determine the structure of a process while carrying on an experiment. And he wrote down the dynamic programming equation for the Bayesian bandit problem, Bernoulli case. And he said, oh, it's quite surprising it is so difficult. Okay? He proved some properties, but couldn't solve it. And then the big breakthrough in the Bayesian bandit problem was this work of Gittins and Jones in 1972. And they came up with an index, and they showed every arm has an index. The problem decouples, and you simply play the arm with the best index. Okay? All right. Now, in parallel, there was also this work on adaptive control, which for a long time was a holy grail of control theory. And the idea is there is a black box, some unknown system, and I want to build an adaptive controller, which I just hook it up to the black box and it controls it beautifully. Okay. So basically, we want to learn the system in real time as we control it. And now, of course, this thing is called part of reinforcement learning. But this problem was looked at by Feldbaum in the Soviet Union in 1960, and he termed it dual control. He said control has two purposes. You can excite the system to learn about it, or you can actually control it, and which is the same as the exploitation paradigm. Now, one big problem that arose in control systems, which was not there in these bandit problems, is the problem of stability. So we're dealing with a nonlinear dynamical system with an unbounded state space. And the fundamental question is, if you connect this adaptive controller, will it blow up? Okay, so is it stable? And this problem of stability actually kept the control field busy for 40 years. And one important development of this, which had enormous industrial success, was Ostrom and Wittenmark's self-tuning regulator. They were motivated by the problem of paper machine control. And they formulated the problem of regulating the paper thickness. Apparently, the better the thickness of a paper is regulated, the lesser the feedstock you have to use, and it has lots of benefits. So they formulated that as an Rmax problem and considered the minimum variance control law, which is the thickness of the paper. And that led to the self-tuning regulator and so on. And there was a lot of fundamental questions. Is it stable? Is it self-optimizing? Is it self-tuning? That took a lot of work. And the problem of stability for the stochastic case was resolved by Goodwin, Ramage, and Keynes in 1981. And then we showed convergence for the stochastic approximation algorithm a few years later. And then Lei Guo and Hanfu Chen in China showed that for least squares. Now, in parallel, in Czechoslovakia, Peter Mandel was looking at the problem of adaptive control of Markov decision processes. So he said, let's consider Markov chains with a state space and an action set and transition probabilities that depend on the action and an unknown parameter theta. And every time you have a transition, you incur a reward. And there's an unknown parameter, and we want to maximize, let us say, the reward. Okay. So Mandel looked at the certainty equivalence control law. He said, supposing I estimate the parameter, then for each parameter, there is an optimal control law. And so let's look at the maximum likelihood estimate and then follow that up with the certainty equivalence control law. And he asked the question, does self-tuning occur? And then what he showed is that if there is identifiability, then in fact it happens. And identifiability simply means that from every state under any action and under any parameter, the outgoing transition probability vector is different. So they're kind of very strongly identifiable. And if that is the case, then good things happen. And that is a problem that motivated Borkar and Baraya. They said, what if this very strong identifiability condition is not satisfied? And then they showed that you have this fundamental closed loop identifiability problem. If the parameter estimates converge to theta star, then the control law you'll be applying is phi optimal theta star. And the true system will be evolving according to this closed loop where the plant is that corresponding to the real parameter, true parameter. Whereas what you think it is this control law, which you know you're applying, and you think that the parameter is theta star, and you will settle on this parameter theta star only if these two are identical, and that's closed loop identification. But unfortunately, this control law phi theta star may not be optimal for theta 0. So that's when, and basically as theta t converges, we stop exploring. Okay, that's the problem. So that's when we looked at this problem, and we discovered that there's a bias of this, fundamental bias of this maximum likelihood estimate. Suppose, and here I'm changing notation a little bit, I'm going to look at reward now, not cost. Suppose V optimal theta is the optimal reward attainable if the parameter was theta, okay? Then the fact that you have equivalence between these two closed loop systems means that the optimal reward for this system, which is V optimal theta 0, has to be reward greater than the reward you incur under this system, because this control law is not necessarily optimal for this. But however, the reward you incur here is the same as the reward you incur here because the closed loop dynamics are the same. So the optimal reward for theta star is exactly equal to this reward. So that means that any parameter estimates to which you converge has to have an optimal reward which is less than or equal to the optimal reward for the true parameter that could be attained for the true parameter. So that's what motivated us to say, hey, can we bias the estimate to favor parameters with higher rewards? Okay, that was the cost biased maximum likelihood estimate, or in this context, the reward biased maximum likelihood estimate. So that was the biasing. So we take the likelihood function and we bias it delicately towards higher rewards, but with a weight with an exponential with an alpha t, which grows slowly compared to t. And we'll see why does it have to go slowly compared to t. Okay. So we want alpha t to go to infinity, but we want it to be little of t. And a delicate balancing is needed because I want to push it towards parameters with higher reward, but I don't want to damage the identification aspects, the maximum likelihood estimate. Okay. So this bias term, V optimal theta raised to alpha t, needs to be small enough that it doesn't damage the maximum likelihood estimator, but large enough that it moves the estimate to have a larger reward. So it's a very fine operation. And I'll give you a rough idea of why this biasing is just right. Okay, neither too hot, not too cold, just right. So first, bias is small enough that it doesn't damage the maximum likelihood estimate. Why is that? So if you take the log likelihood, the alpha t comes in the out here, and then you get log of V optimal theta. Now this term grows like little o of t because alpha t is little o of t. On the other hand, this term grows like t. So the biasing doesn't damage the identification. Okay, roughly that's the intuition. At the same time, it's large enough for the following reason. Okay, so you have this biased maximum likelihood estimate, and I'm going to normalize it. So as we all know, maximizing the likelihood or maximizing the likelihood ratio is the same. In fact, you can divide the criterion by anything that doesn't depend on theta, and the maximizer will remain the same. In this case, we divided by the biased maximum likelihood under the true parameter. Okay, so that's the same thing. Now, if V optimal theta is less than V optimal theta 0, then this fraction is less than 1, and because alpha of t is going to infinity, this ratio goes to 0. On the other hand, this thing for any particular parameter is a positive martingale, okay? And therefore it's converges and it's bounded, and therefore the product will converge to 0, okay? Now, on the other hand, if you choose the parameter estimates converging to theta 0, the maximum is always greater than or equal to 1. So essentially, you cannot converge to parameters which have a lower optimal reward, okay? Now, the argument is much more complicated than this because we're not dealing with one martingale, we're dealing with a family of martingales, and I have to take the maximum of the martingales, and that causes a lot of issues, and spent many months investigating that in the 80s and made some extensions, okay? All right. Now, this idea has, this is one of the ideas that was picked up by the machine learning community. So we had done this adaptive controller for linear quadratic systems and so on. And that got a little bit of traction in the machine learning community. But by and large, they're not aware of this bias maximum likelihood estimate. Okay, so let's go back now to multi-arm bandits and revisit this whole problem, okay? So around 1985, Lai and Robbins introduced a finer notion, okay? The finer notion of regret. They said, hey, listen, let's look at how the reward deviates from the optimal total reward. And the question they asked was, how small can we make this regret, okay? And they showed, beautiful paper, they showed that the optimal regret is C log T, okay? And they also came up with a policy that attains this optimal reward. And this is very well known in machine learning now. It's called the upper confidence bound policy. And what you simply do is you define a high probability upper confidence interval for each parameter. So for example, for each arm, there's an interval, and with high probability, I can say that it is less for arm 1, the parameter is less than J1 of T. For arm 2, it's less than G2 of T, G3 of T, and so on. And G1, G2, G3 are called the upper confidence bounds. And they said, let's play the arm with the highest upper confidence bound. Okay? And the rationale for that is the following. If an arm is not explored enough, so you play an arm very few times, then its confidence interval is very large, uncertainty is very large, so its upper confidence bound is very large, so you tend to play it, to learn about it, okay? So in that way, it balances this exploration versus exploitation. On the other hand, if you play an arm lots of times, then the confidence interval collapses to the mean, okay, by the law of large numbers. So that was the trade-off between exploration and exploitation, okay? Okay, so where are we right now? So currently, the empirically, a lot of experimentation, the empirically good policies for minimizing regret. One is still Thompson sampling, and you play an arm with the probability that it is the best one. UCB, upper confidence bound, which has now been simplified to a very simple form. And then currently the best candidate until now was this information-directed sampling introduced by Russo and Ben Van Roy. Ben was John Tsitsiklis's student. And that's a heuristic. It says, hey, listen, I'm interested in exploration. I'm also interested in exploitation. So exploration means I want to maximize the information about the optimal choice. Exploitation means I want to reduce the expected regret. And I will have both these criteria. So I'll form a fraction, a ratio where I want to minimize the conditional expected regret. That's the exploitation part. And then I want to do the exploration part. I want to minimize the entropy reduction with respect to the optimal arm. So they suggested a heuristic, and they said, let's use this as a criterion. One issue with this is that it requires computation of very high dimensional integrals, and they say that there's much more work to be done to design efficient algorithms. So these are roughly and some variants of these are roughly the best contenders for empirical performance in Bandits: Thompson sampling, UCB, and information-directed sampling. Now, both UCB and the cost bias maximum likelihood estimate fall, but this phrase was invented, is a more recent phrase. It's called optimism in the face of uncertainty, and it's been applied to UCB. But it's also true of the earlier cost biased maximum likelihood estimate, though it does it in they do it in different ways. The cost bias maximum likelihood estimate deliberately biases maximum likelihood estimates towards arms with larger theta because of the bias of maximum likelihood. Whereas UCB deliberately prefers arms for which there's a chance that the theta could be larger, the upper confidence bound, okay? And there has been a lot of testing of UCB and Thompson sampling over the years, but absolutely no follow-up on this cost bias maximum likelihood estimate. In fact, machine learning community is unaware of it, except for that stray thing that followed up in linear quadratic thing. And the question therefore arises, what is the regret guarantee that you can give for cost bias maximum likelihood estimate? How does its regret perform empirically, and how does the computation scale with the number of arms? Now, I should tell you a little bit about this notion of regret. So after we did this work, a few years later, Lai and Robbins came up with the regret, and I was completely aware of their work, but somehow I never connected the dots with our work for the following reason. I was always thinking in the following way. I was saying, listen, if you're interested in almost sure behavior, I can rarefy the sampling as much as I like. So it kind of, I was not very interested in the rate of rarification. But what I missed was that when you put an expected value there, then it does become very interesting. Okay, so I missed that strand. So anyway, so last year before, when Shilu said, hey, let's look at machine learning, I said, okay, let's look at this problem. So we revisited this whole issue, and we now want to clean up regret and everything, empirical performance, and I want to tell you how it performs. So let's consider the exponential family of distributions, exponential family bandits. So I'm considering distributions, one parameter exponential families, and they have beautiful properties. So these are parameters where the probability of getting a reward X has a certain exponential dependence on an unknown parameter theta. It can be shown that A theta is strictly convex, and the mean value is the derivative of A. And because it's strictly convex, A prime theta is strictly increasing. Now, for this whole exponential family, since I want to bias the reward, I have to put in A prime of theta here because that's the mean. And in fact, I can take any monotone function of that because I just want this order relationship in biasing. And I can use this M, actually take it to be the inverse of A prime because inverse of strictly increasing, and actually simplify this whole business. And it turns out that we can get explicit indices for this whole family. Okay, so we get explicit index solutions, nothing very complicated. And then you simply play the arm with the largest index. Okay, so this comes up, this is very different from Gittins and Jones because that's a Bayesian formulation and it's a specific index forced by the criterion. And here we just get an index in the non-Bayesian frequentist case. Okay, and you can easily calculate the indices for common distributions. So for the Bernoulli bandits, this is a distribution that I had written down in the 80s. And for exponential bandits, the index is very simple. What is striking is that all it is basically like the empirical thing, except you introduce this bias in the denominator for exponential, you introduce this bias in this maximum likelihood for Bernoulli, and in the Gaussian case, you just add to the numerator. Very, very simple modifications of something empirical, okay? Very simple. Okay, but can they perform beautifully? That's the question, okay? Now, we have not proved any regret bounds for that, so made up for that. So first, expected bound on regret. Supposing I knew a lower bound on the difference between the best term and the second best term, the capital delta difference, then it turns out that if you choose alpha t to be C log t, where C depends on this difference, then you can get log t of regret, okay? Now, if you don't know this difference, then in the Gaussian case, you can adaptively estimate it, and that gives you, and then you can again get log t regret. On the other hand, if you don't know in general, and this is something we're still working on, if you don't know the lower bound on difference in the general case, even then if you take alpha of t, the bias to be gamma t log t, where gamma t grows arbitrarily slowly to infinity, then you can get gamma t log t. Very good. You can also get sample path bounds on regret. For every delta and for every c positive greater than 1, there's a non-random k, so that the probability that the number of wrong place in 0t, which is regret, is less than C alpha t plus k is larger than 1 minus delta. So you can get a packed type of bound. Okay, so now let's see what the performance is. So empirical testing. So here is a Bernoulli bandit. I don't know how many there are, maybe 10 bandits. And the bandits are also finely, there's very delicate differences between them. They differ only in the second decimal place, their successes. And what I'm plotting here is the average over 100 trials, the cumulative regret as a function of time horizon. And what we find is that this cost bias maximum likelihood estimate, which is this BMLE, actually appears to have better regret than many of these others, at least in this particular example. And the closest contenders happen to be IDS and VIDS, information directed sampling, and modification of that. Okay, so that's over here. And also good is Thompson sampling. Okay, still after 70, 80 years, still good. And pure UCB doesn't do so good. It's theoretically it's very nice, but its regret actually is much worse. So this is the regret performance, but we're also interested in computational complexity, okay? Because we are living in a Google era where the number of arms could be thousands or tens of thousands, right? Google has to choose from a whole bunch of them, which one to choose. So what I'm plotting here is on the y-axis is the computation time per pull, and the x-axis is a regret. So ideally, I would like a policy which is right over here because it would have very low regret and very little computation time. And it turns out that cost bias maximum likelihood estimate is in that lower quadrant here. Now, in fact, if you don't do this modification with the adaptive version, then its computation time is actually somewhere here. Okay, so it's pretty much close to the best. Now, other contenders like VIDS and so on are a little bit orders of magnitude more computationally complex. We can also look at the statistics. We can look at the various quantiles and so on. And the bias maximum likelihood estimate does seem to do better than a bunch of these. These are the regrets of leading contenders, KL, UCB, Thompson sampling, Moss, etc. In the case of Gaussian case, again, seems to do pretty well, regret. And in the Gaussian case, because we have such an explicit simple formula, the computation is also not that much. So it's got low complexity and low regret. And again, the statistics are pretty good. And in the case of exponential bandits, again, it's pretty good. And again, low computation and low regret. Okay, so before I conclude, just some broad remarks. So with respect to bandit problems, regret is very important financially to companies like Google, but in the present era, also very important for individuals sacrificed, as Thompson put it. So it's an interesting, it's important optimization criterion. Also, scaling of computation is important in Google size applications for real-time implementation, okay, where you have to show the results as soon as a user presses the search key. Now, there are many extensions of this reward biased maximum likelihood adaptive control. The first adaptation I want to make is I want to, instead of calling it cost biased, let's call it reward biased. The applications we can apply to contextual bandits, Bayesian optimization, model-based reinforcement learning, etc. The advantage is that it gives you a, for things, anything that can be modeled as a Markov decision process, it gives you a procedure. The one issue though is the biasing has to be easily computable, and that is a challenge, but it is a generalizable framework. Okay, so there's a lot of work to be done, and I will stop there. Thank you very much.
Thank you so much, Professor Kumar, for the presentation. I think we have a few minutes, for a Q&A here. And I guess we're going to do the Q&A is that you guys can either write in the chat here if you have questions, or you can use the raise hand function in Zoom to raise your hand. I will call your name and you can ask the question. So maybe while we give the audience time, to figure out the comments and how to ask questions, let me ask with let me start with a simple question here. So I was curious, in slide 46, 47, there are a couple of other approaches which are very competitive. If you can go back to that slide, I was curious about which approaches are these. 46, 47.
Oh, 46, 47. Hold on one second. Yes. This is 46.
So I think there is this, maybe the previous one, there's an approach which is going pretty well in the previous slide, which I think is this, the crossover, the RTS can you comment on the differences? Because there are approaches which are pretty computationally efficient here, and they are performing relatively well.
So I think that probably it's fair to say that all the policies over here are pretty much top tier policies. Okay, mm-hmm. All of them over here are top tier, and probably fair to say that these policies are not competitive. Okay, the distinctions here are kind of minor. Okay, and yeah. So I guess, and I would also say that these computations here are pretty much good. Maybe something over here would not be good. Okay, scale in terms of scalability. I think the contribution basically is that there is another approach. So far, the only approaches we basically know are UCB and Thompson sampling. Okay, and here is another approach: cost, bias, max, and likelihood estimate, which also is generalizable to MPP, which also seems to have good performance. And I think that one needs to evaluate it in different contexts. So we're just adding another contender to the scene. That's all. Okay.
Got it. Okay, I saw John raising his hand before. So John, maybe you can unmute yourself and ask the question.
Okay. Thanks, Kumar, for a great talk and also great perspective. I think the results sound definitely very, very good, but I think there's also a meta message in what you said. And so the question is, what would be your advice to a beginning graduate student who has two extreme options? One is to go back and look at all the literature of the last 50 years. And the other extreme is to look at the last NIPS paper of somebody else and run for the conference deadline to produce the next paper. So how is one to navigate, especially now that there's so much information out there?
So it's a question about exploration versus exploitation, I guess.
Yeah. Well, I think, can I go even one step beyond John's question and extrapolate even further? You know, facts and knowledge and so on is growing exponentially. Okay, the number of papers, etc., is growing exponentially. Yet, the time that we have for an undergraduate education, at least in my day, it used to be 5 years, and now it's 4. So it's actually shrunk a little bit. So we still have 4 years, but we have more and more topics to learn and so on, right? So ultimately, from an education point of view, I think that down the road, we are probably going to, what we teach is we'll teach people how to teach themselves, okay? So we'll just say that, hey, different fields have different styles of learning. For example, if you are in philosophy, this is the way you approach issues. If you are in law, this is the way you approach. If you're in systems, computer science systems area, this is the way you approach it. Where systems theory, you'd approach, and so on. So maybe we just teach styles of learning and so on. So there are some questions regarding here to education. Now, John's question is actually more towards the research end, the graduate student end. I think it is important. Actually, I think it is important for students to learn fundamentals and basics of fields. So, I mean, right now, people in machine learning well recognize that statistics is very important. And in fact, statistics, the popularity of statistics and the importance of statistics has grown a lot together with machine learning. Same thing with optimization. You know, optimization somehow was kind of neglected in some sense for many years, but now it's a very exciting area, okay? So, and these are fundamentals, right? Statistics, optimization, maybe dynamics, maybe decision-making, etc. So these are fundamentals, and I think people should learn, should be well grounded in the fundamentals. And of course, the latest NIPS papers also are very important for the following reason. You know, in general, the systems area, and say computer science or experimentation, they kind of calibrate what we can do. Can we solve this character recognition problem? Can we solve this automobile vision problem, etc.? So it kind of calibrates what is feasible, and that's also important, okay? So I think both these are important, and there's a kind of a creative tension between them. And that's what actually makes it interesting, right? I mean, you kind of flip and flop on both sides, and that's where the creativity probably is. I'm not sure I answered your question, but so just some ramblings.
Let's see if you have other questions here. Again, if you participant, there is hand button that you click if you want to ask.
You know, maybe
So
just I can add something to what I just said to John. So for example, if you take say machine learning, right? Take say support vector machines versus say deep neural networks, right? Now, actually in the 80s, I had kind of written off deep neural networks. The word deep was not there, right? And I said, wait, this thing is non-linear, non-convex, blah, 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 and nobody knows what's happening and so on. But I have to give a lot of credit to, say, Jan LeCun and so on for persisting with it and so on, and building in the invariances of the domain, whether it's shift invariance for convolutional neural networks or whatever, right? Building that structure in, domain knowledge in, and actually showing that this thing can work. At the same time, you have to also look at Vapnik's work. You know, Vapnik's beautiful work on packed learning. And I mean, I remember Vapnik visited me in the 80s soon after the Soviet Union kind of imploded and exploded. A lot of scientists left the Soviet Union, and Vapnik came to Bell Labs, and he came to visit me, and for a week or two. And he was saying, boy, you know, in the old days in the Soviet Union, we wrote one paper every 5 years. But now whenever he passed somebody's office in Bell Labs, they were writing a paper. You know? So he was quite amazed at that. Now he developed a field with a very long-term objective. I mean, proving theorems on uniform convergence in the law of large numbers, anticipating its usage for machine learning many decades hence, and then his beautiful work on support vector machines and so on. Very beautiful theoretical stuff, and they were very competitive with neural networks until this convolution thing came over and so on. But so there again, there's a tension, right? The theory and the practice, and I think it is too soon to write off, say, the theoretical approach of support vector machines. There's still I mean, deep neural networks require a lot of data, whereas support vector machines can also function well with lower data. They have a little bit more explainability, etc. So just because they've been successful, say, in vision or in natural language processing, the game is not over yet. You know? So I think this tension, theory, practice, experimentation is actually quite interesting, even in this area.
So I have a big question, which I was curious about. So do the results that you were discussing in this presentation generally to the case that being time varying? It is time varying here.
I'm sorry, I couldn't understand your question. Can you repeat?
Theta, if the theta that you want to identify here becomes time varying, time, is that like a huge stretch? Is a different theory, or the results will be?
No, supposing theta, let us say, is time varying, but the time variation is characterized by a parameter, say. Let's say it's quadratic, right? It's characterized by ax squared plus a theta squared plus b theta plus c or something. Then the problem becomes identifying again ABC, which becomes a new parameter. So if you know some structural form of the time variation, then you could again convert it to some parametric problem. I think the broader principle is that, you know, if you can write down the likelihood function through some suitable reparametrization or something, then you can again go and attack the problem. I think that's the general approach. Yeah.
Thanks. Okay, that makes sense. All right, guys. I think we are at 4 p.m. at this point, 4 p.m. sharp. So was be just a round of applause in general. Like, you know, in normal situation here, we'll have to be satisfied with a virtual applause in this case, but thank you so much, Professor Kumar, for the great presentation and for staying with us. And thank you, everybody, for attending.
Thank you, everybody. And
Thank you,
look
Kumar.
forward to seeing you all in person one of these days.
Looking
Bye-bye.
forward.
Bye-bye.
Bye-bye. Take care.
Take care.